Our very last technique before we move into vector value differential equations is going to be a topic called reduction of order. And we've seen this kind of a little bit already, and I just want to go through an example to work out how to do it more generally. The basic idea is if you have an order n equation, you can turn it into maybe one, maybe more equations of lower order, like order n minus 1, or if you keep doing that, you get all the way down to 1. We saw in the last video how to handle linear equations of order 1, so we should be done at that point. So I'm going to do this in the case of order 2. The general principle, though, is the same. The first step, as you may have realized at this so far, is to solve the associated homogeneous problem. The trick with this is actually we only need one solution. So this is a second order associated homogeneous problem, so it will have a two-dimensional solution space. Turns out we just need one of them. I guess it shouldn't be 0. If it were 0, that wouldn't be very useful. Sometimes find means guess. Sometimes it means that I just tell you one. Sometimes find means you sort of glance at it and you just see one. Okay. The second step is sort of like variation of parameters. What we're going to do is just say, okay, well, look at all multiples of y1, where u is a function, and see if I can come up with an equation that u has to satisfy. Let's see this in an example. Okay, so you can see this equation is definitely non-homogeneous. It definitely has non-constant coefficients. Let's write down the associated homogeneous problem. Since that's homogeneous, it's really easy to clear that first coefficient. And at this point, we can maybe just guess a solution. You know, we might ask, are there any solutions of the form x to some power? If you just plug the form y to the r into this equation, you'll see that I think r has to be minus 1 in order for this to work. That gives us our y1. Okay, so our general solutions will look like u times 1 over x. So let's try to plug that form of a solution in and see what u has to satisfy. To do that, we need to know y prime and y double prime. Once we know y prime and y double prime, we just plug them in. And if we simplify that, we get x u double prime plus u prime. Now, what do we want about that? We want that to be the same right-hand side as the original equation. And so you can see this is a differential equation. Now, at first glance, it looks like it's second order. It involves u double prime. The important thing, though, is that there's no u's here. There's just u double prime and u prime. So you can think of this as a differential equation whose variable is u prime. The easiest way to write that down is just to pick a new variable. Let's call it w. Is going to be u prime. And we can rewrite this equation as xw prime plus w equals 4 log x. Now, that's a first order equation. We know how to solve first order equations. We could go through the trouble of finding an integrating factor, but I think if you glance at this really quickly, you see that that left-hand side is just the derivative of x times w. Okay, now we integrate that. And since this is the right-hand side, we need to make sure we put that c there. Because this is second order, I expect to have another constant somewhere along the way, so I'm actually going to call that c1. All right, so then what's w? Okay, so we have w. Let's clean that up. W is u prime, and we really want to find u. What's u? Well, you integrate. And since we've integrated, we need another constant of integration. There we go, that's u. So what's our general solution? It'll be u times y1. And remember, y1 is 1 over x. So we just divide everything through by x. And there you go. You can see we've got two independent constants, c1 and c2, representing the fact that this is a second order equation. So the solution set is two-dimensional. You can check it. Maybe it takes a little bit of differentiation to check it, but it works.